a bit of error mitigation and all of those things. Today's session will be slightly more mathematical. What I will request you all is to kind of walk with me as we go through these three things. We will first understand what is entanglement. We will go into teleportation, super dense coding, and CHSH game. All of these are really important and interesting things of quantum computing.
Ritajit sir, you are not audible.
Uh, Not audible? Okay, just a minute.
Hello.
अच्छा अपने आप
ये अपना issue है देखो.
अपना
Okay. Okay. No, it seems I am audible. The others are saying so.
yeah
Okay. So what
Yeah, please go ahead.
Yes, thank you. So what I'll do here is that we'll walk through all of these. As I said, these are very interesting and important topics of quantum computing. What I will request you all that since this is going to be slightly more mathematical than the last session that I did on QT-03, it was more hands-on kind of thing. So please walk with me, and I have deliberately left some questions. Some of the questions are definitely more complicated and will require you to go back and try things out yourself. But some of the questions we should be able to answer over the call. And I would really encourage you that when we come to those questions, please use the chat box or unmute yourself to give the answers, however way it works or is more suitable for you. So let's go into this very fascinating idea of quantum entanglement. Perhaps you all know that if you don't, this is very interesting that Einstein called these spooky action at a distance. And he was not very comfortable with quantum mechanics. And he kind of suggested what we will see today, what is entanglement. He kind of suggested that these kind of things, that is entanglement, is not really coming from quantum mechanics, but there is something missing from the theory. There is some hidden variable, and if we can know that hidden variable, so he suggested this theory is incomplete, and if we know that incomplete piece, we will be able to describe everything that is going on perfectly. And this particular CHSH game is something which we will show is kind of disproves Einstein. It proves that Einstein was wrong here, and the Nobel Prize in 2022 came for the demonstration of this experimentally. And teleportation and super dense coding, these are again coming from Charles Bennett, who is from IBM. He's still in IBM. And it's funny hearing from him. He told us once that how he did it, that when he started doing it, nobody really cared. I mean, they thought these are kind of some stupid things that he's working on. So he used to do his entire day job, and then he would go back and do all these calculations. And today we even have this IBM quantum branch, so started by him. So let's get started with this. Multi-qubit system, we know that, let's say that I have a 2-qubit system and the individual qubits are psi A and psi B. It's usually very general to call them Alice and Bob, so I'll use that convention, and I have used A and B in that sense also, that say this is with Alice, this is with Bob. So if I ask what is the joint representation of these two qubits, it is always the tensor product. So psi AB is psi A tensor psi B. So I can represent the joint state of Alice and Bob using the tensor product of their individual qubits. The question that we will ask today, that is the reverse always true? So if I give you a joint 2-qubit state, psi AB, can you always find psi A and psi B such that this tensor product things holds? So this is the question that we will look into today. So let's take a very simple example. So let's say that psi A, it's a 2-qubit system. So 0, 0, this is a valid 2-qubit system, and it's a tensor product system. So we will call these states as separable. So it's a tensor product system. I can definitely write down what is the state of the first qubit. I can definitely write down what is the state of the second qubit. Same for psi b, it is 1, 1. So I know that the first qubit here is in state 1, second qubit is also in state 1. So these are valid quantum states. Now, so what you have already seen is that if I have two quantum states, then any linear combination of those two states is also a valid quantum state. This comes from Schrodinger equation itself. So what does that mean here? It means that since psi A is a valid quantum state, psi B is also a valid quantum state, so is something like this. As long as, so A and B are some coefficients, as long as mod A square plus mod B square is equal to 1, and I am assuming here A and B are not equal to 0. This is an assumption which will come handy in our next slide, you will see. I am assuming that these are not trivial superpositions. These are just like proper non-trivial superposition. A and B has non-zero values. So as long as this is a unit vector, this is also a valid quantum state. So what does that mean in terms of this particular um, qubits? So I can write psi AB as A00 plus B11, and this is a valid quantum state by what we have seen so far. So now the question is that if I give you this psi AB, which is of this form, can you find me psi A and psi B such that you can write psi AB is a tensor product of those two states? Think for a second before we go to the next slide. Can you really, so what we need to do is factorization, right? This is tensor product, but it's basically the other way is factorization. Think for a second to yourself that with this particular state that we have, can we really factorize this to find psi A and psi B individually? Yeah, so I'll take a 30 seconds gap maybe. Yes, we can. Okay. So one answer I saw is we can. Anyone? Okay, so that's interesting. So we have yes, no, all types of answers here. So let's actually try to do it. And we will assume that we can factorize it. This is the assumption that we will go with. Let's see. So if I can factorize it, then I should be able to write it like this. So this portion belongs to Alice, this portion belongs to Bob. I should be able to write it down like this. All I need to find is now the other values of these coefficients, right? So let's look into what we have. So if we do this multiplication, this AA times AB is equal to A. Similarly, AA times BB is equal to 0 because there is no 0, 1 state here. Similarly, BA times AB is also 0 because there is no 1, 0 state here. And BA times BB is B. So these are the four equations that we have got, and let's try to solve these equations. So let's look into the third equation. I mean, you could have started with the fourth equation, doesn't matter. Let's look into the third equation. So product of these two numbers is 0, which implies either both of them are 0 or at least one of them is 0. So let's take the scenario where at least one of them is 0. So if AA equal to 0, then it immediately means that small a is equal to 0. But if you remember, I kind of emphasized that I am looking into a state where A and B are not equal to 0. So if I say that AA is equal to 0, then 0 times anything is 0, so small a is equal to 0. Or if you say BB is equal to 0, then BA times 0 is equal to 0, so small b should be equal to 0. So it means either small a is equal to 0 or small b is equal to 0. But we kind of said that both of them should be non-zero, so it's a violation. So what is the verdict that we get from here? So here we have a mathematical representation of a composite 2-qubit system. We have a very nice mathematical representation. we know that two component systems exist. Of course, they exist. It's a 2-qubit system. So the two individual qubits exist, definitely. But we cannot mathematically represent the individual component systems. And we can take them all together and say this is kind of entanglement. So if we repeat again that we have a 2-qubit composite system, definitely. We have a very nice representation of that. There is nothing missing out of here. We know this is a 2-qubit system, so there are two individual qubits which are existing, but mathematically we cannot represent that. Mathematically, I am unable to tell you what is the exact formulation of the first qubit, what is the exact formulation of the second qubit. Yes, if some of you have already studied other stuffs, you would know that there is something called density matrix representation here, which can help you with this kind of representation. But at least in this bracket notation, we are unable to give any mathematical representation of qubit 1 and qubit 2, even though we know very well that the qubits exist. So this together, we can say is that the system is entangled. This system is entangled. Okay, awesome. So, and this is very, very counterintuitive, right? That things exist. I know they exist. I cannot represent them. So let's look into some properties here. So this was my system and I know this is entangled. What happens? So what can happen? So Alice is in her lab, Bob is in a different lab. Let's say they need not be in the same lab sitting next to each other. They can be in one city, another city. Sometimes I like to say that Alice can be in Earth, Bob can be in Pluto. But Alice measures her qubit in the computational basis. So that means the outcome will be 0 or 1. So what happens if she measures her qubit? Of course, she will obtain 0 with probability mod A square or 1 with probability mod B square. That's all fine. Like there is nothing I am saying that you don't already know. But let's look into the next question. What happens to Bob's qubit when Alice measures her qubit? So Bob is not doing anything to his qubit. Alice and Bob are not sitting at the same place. So Alice cannot do anything to Bob's qubit. But what happens exactly here? So let's say that Alice measured her qubit, it collapsed to 0. Then this entire state should collapse to 0, 0 because we are definitely sure that when Alice gets 0, her qubit is not in state 1. So this entire portion gets cancelled. So when Alice's outcome is 0, the entire state has collapsed to 0, 0, even though Bob has not measured his qubit. Bob may not be in the same physical location. So as I said, Bob can be in Pluto, Alice can be in Earth. Same, if Alice gets the outcome 1, Bob is definitely going to get 1. The state has collapsed to 1, 1 because this part has cancelled out. Entanglement. So that's the property that it's property of entanglement, that measuring one qubit hampers another the state of the other qubit. It changes the state of the other qubit, even though there was nothing done to the other qubit and they may be spatially separated. So something I will leave for you. You should try it out, not immediately. It's not something you can do just on head. Verify that if we have such a tensor product state, and if Alice measures her qubit, it does not change the state of Bob's qubit. Here it does. Here, remember, we couldn't give it such a nice Xi A tensor Xi B representation here. Here, definitely it does. Measuring one qubit affects the other. But if we could give such a nice representation, so that means the state is not entangled, just give it a shot, and it's actually easy to show that if Alice measures her qubit, it does not change the state of Bob's qubit. But let's move on. Like this is something you can try and it's not very difficult. Let's look into another property, and this is something very interesting. So we again have a state like this. And previously I said Alice measured in the 0-1 basis, the computational basis. Now let's say Alice is measuring in some other basis. Let's say Alice is measuring in the X basis. So if you don't remember right now, the eigenstates of X basis are plus and minus. Plus is 0 plus 1 over root 2, minus is 0 minus 1 over root 2. So when Alice will measure in X basis, the outcome will be either plus or minus. What happens when she does this measurement? So let's do a bit of mathematics. So plus is 0 plus 1 over root 2, or the other way you can write that 0 is plus minus by root 2, 1 is plus minus minus by root 2. So what I'm doing is I'm just writing this state in plus minus basis, and I have just decomposed it. It becomes something like this. Now here is something very interesting that will happen. So this is the state that we get psi AB. Now I can find out what is the probability that both the qubits are plus, one qubit is plus, the other is minus, or both of them are minus. So the square of this will give me the probability. Let's say A is equal to B. If A is equal to B, then they should be 1 over root 2, right? Okay, I think there was a question that how do we know? So if you measure in X basis, if you write down the matrix of X, that will be 0, 1, 1, 0. If you find out the eigenstates and eigen values of that, you will see that these will be the eigenvectors. So if A is equal to B, definitely it should be 1 over root 2, both of their values. If that is the case, then A minus B is 0. A minus B is 0. These two terms gets cancelled out. So I get something like this. What happens if Alice measures this? She will get plus with probability half, minus with probability half. When Alice gets plus, Bob's qubit has also collapsed to plus. When Alice gets minus, Bob's qubit has also collapsed to minus. So this has the exact similar properties of what we saw 1 over root 2, 0, 0 plus 1, 1. The same property it retains, so it is still entangled. Like having the outcome of one qubit, measuring one qubit affects the other qubit. So it is still entangled. On the other hand, if A is not equal to B, I have all the four terms, and if I give you the values, you will be able to factorize it and write it down as Alice's portion tensor with Bob's portion. So when A is not equal to B, this state is not entangled. What does that mean? So if my A and B are both 1 over root 2, so that means A is equal to B, you can try to show, I have shown only in the X basis, you can definitely try it out that instead of X basis, if you come and say I'll do it in Y basis, if you say I'll do it in some sigma basis, something totally different than XY or anything, this particular state remains entangled in any basis where you want to measure. So you should definitely try to prove this. On the other hand, so such a state is called a maximally entangled state. A state which remains entangled in any basis is called a maximally entangled state. On the other hand, when A is not equal to B, so that means it was entangled in the 0, 1 basis, but it is no longer entangled in the plus minus basis. Such a state is called a non-maximally entangled state. So it is entangled in one basis. If some one of you are from the physics, so we can think of this, that this is entangled in any spin direction that you want to check. This is entangled in only one spin direction, not in other spin directions. So this is maximally entangled state. This is non-maximally entangled state. So now if we look into, so this is the state that we talked about, that it is maximally entangled. You could replace 0 with this plus with minus also, nothing changes. So the probability still remains the same. You could have taken 0, 1, 1, 0, still the same. So what will change here? When Alice gets 0, Bob gets 1. When Alice gets 1, Bob gets 0. And similarly, you can add a phase of minus here. These four states are called Bell states. And something that you can try out, definitely try this out, is that these four states form a basis. So that means if you have a 2-qubit quantum state, then it can be expressed as a linear combination of these four states, whatever 2-qubit quantum state you have. That is point one. Then this is very important. I mean, both of these are very important. The point two is these four states are orthogonal. So if you take the inner product of any two of them, they are orthonormal, because if you take the inner product with itself, it's one, but that's like the requirement that it needs to be, the norm needs to be one. If you take the inner product of any two states, it will always give you zero. So that means that these four states are orthogonal. So you can measure in this basis. You can create a projective measurement. So just like you can measure in 0, 1 basis, because 0 and 1 are orthogonal, you can measure in plus minus basis because plus and minus are orthogonal. Similarly, you can measure in these four states and forming a basis here. Let's look for an example. Let's say that psi is 0, 0. Can you measure it in this basis? Yes, it turns out yes, you can. So how do you do that? See, I can very easily represent 0, 0 like this. So this is 1 over root 2 psi plus psi minus. So if you do this plus this 1, 1 gets cancelled, right? And you are left with only the 0, 0 portion. These two will have coefficients of 0. So now if you measure in this Bell basis, we'll get the outcome psi plus with probability half, psi minus with probability half. So what does that mean? Let's look into this. This has two meanings. First, the simple thing that I talked about, that you can measure in this basis. This forms a basis. The second thing is, if you measure in this basis, for this example, we started with a state 0, 0 that was not entangled, that was a separable state. But if we measure it in Bell basis, it will collapse to one of these four states, right? Here we see that these two have coefficient 0. So with 50% probability, it will collapse to this state. With 50% probability, it will collapse to this state. It will become an entangled state. So you can actually measure in this type of basis, take a non-entangled state, make it entangled. So if you have heard, there is a huge branch of study that's called measurement based quantum computing, where you can give proper measurements and change the state of the system. So you see here, I have not applied any gate or anything. I have just taken a single 0, 0 state. I have measured it in a nice basis, and I am getting entangled states. So this is a very interesting idea here. And this is a slide where I want to spend some time. So these are the four Bell states that we just talked about. They form a basis. How do you go from one state to the other? Let's spend some time on this. Let's look into how I want to go from here to here, or the other way, here to here. It's the same. So see, I need to add a phase of minus, right? And if you remember that Z gate acting on 0 does nothing. Z acting on 1 gives a -1. So here, on which qubit do you want to apply the Z gate? Say I am applying it on the second qubit. It will still give a minus here. Say I am applying it on the first qubit. It will still give a minus here. This is something very, very important that will come very handy when we talk about teleportation, dense coding, and everything. What it means is that it doesn't matter whether Alice applies the Z gate or Bob applies the Z gate. Any one of them can apply the Z gate. The state will change from here to here or here to here, right? If this is fine, I would encourage you to just give a second to think what will happen if it goes from here to here. What gate do you need to apply? Any thoughts, comments? Yes. Yes, excellent. So it's X gate. Who needs to apply the X gate? Again, anyone. Not X basis. It's not X basis. It's X gate. So just one correction. So when we do measurement its measurement occurs in a basis and the system collapses in the eigenstate of those bases. So here I am talking about X gate. It can be either Alice or Bob. So see, the reason that some of you are saying that it should be Bob, because my zero, the second zero has changed to one, second one has changed to zero. What if Alice applies? It will become 1 0 plus 0 1. That's the same thing. It's commutative. So again, either Bob can apply or Alice can apply. So if Bob applies, the second 0 goes to 1, second 1 goes to 0. If Alice applies, then 0 goes to 1, 1 goes to 0. Then it it simply becomes 1 0 plus 0 1. That is fine. Not a problem. Let's ask the same question for this one. Which gate? I'll tell you which gate. It's definitely Z gate. I mean, it goes from plus to minus. Who can apply it? Alice or Bob or both? That's the interesting question here. Bob. Okay, there is one answer that says both, and everyone is very much towards Bob. Okay, I see why most of you are thinking Bob, and that's totally valid. So, Bob, see, Bob has the second qubit, right? So ideally, if you want to make it minus, you need to apply a Z gate on this. So Alice, if you apply a Z gate on the first qubit, nothing happens here. This changes to minus. Alice, done. What happens if Bob applies? Bob's action will make this as minus and keep this as plus. So it becomes minus 0, 1 plus 1, 0. Take the minus common. It becomes minus in bracket 0, 1 minus 1, 0. So you can say that this minus is now a global phase. I don't care about that. So it's still 0, 1 minus 1, 0. So again, both Alice and Bob can apply. Similarly, let's not keep making you right again and again. Similarly, you can see this will be X gate. If Bob applies, it's immediately fine. If Alice applies, it becomes 1 0 minus 0 1. But again, you can take the 0 common and it becomes 0 1 minus 1 0. This one becomes a Y gate. So XZ is proportional to Y. And similarly, this becomes YZ. XZ is proportional to Y. What does this mean? Why did I spend so much time on this particular slide? What it means is that you can go from one Bell state to another Bell state using a single Pauli operation. So if you remember Pauli operation, identity X, Y, Z. So I can go from from any Bell state to any other Bell state using a single Pauli operation. Even though I have written XZ here, it's basically Y, right? And it doesn't matter whether that Pauli operation is performed by Alice or it is performed by Bob. Any of them will work. So this is kind of the take-home message from this slide, that we can go from one Bell state to another Bell state using just Pauli operation. And it doesn't matter whether Alice applies the Pauli operation or Bob applies the Pauli operation. Okay, so if there are any questions, I think this is a good point to take the question before we go to teleportation. Just stop sharing for a moment. Okay. Yes, Bell states are defined. So, okay, let me look into the questions once. Okay, so the first question is, does it mean superposition cannot be represented as a tensor product? No. So I can always have, say, alpha 00 plus beta 01 plus gamma 10 plus delta 11. And for good values of alpha, beta, gamma, and delta, I can always represent it as a tensor product state. So it is not true that no superposition state can be represented as a tensor product state. In fact, most of the superposition states can be represented as a tensor product state. However, if no, I'm not sharing screen at this point. However, if there are some states where you cannot represent it as a tensor product, those states are called entangled. So yeah, so I hope this answers your question. Yeah, I'm not sharing the screen for now. There was a second question. Bell states are always entangled. Yes. So Bell states are defined as those states where uh, the entanglement is retained in any spin direction. So Bell states are always entangled in any spin direction that you measure. No, so I'm not sharing the screen at this moment. While entanglement can exist in other qubit systems as well, why is Bell state only reserved for a 2-qubit system? So no, okay, Bell state is a very special name given to a 2-qubit system like this, but you can actually go to multi-qubit system and it's called G8Z state. So it's not like that it is only for 2-qubit system. You can find a similar maximally entangled state for n-qubit systems as well, and it is called G8Z state. For only for 2 qubits, it is called Bell state. Okay, so the problem is if I start sharing the screen, I cannot see the questions. Okay, I'll come to this, how to understand which one Alice or Bob can apply. Is it mainly for communication? Definitely. So what we will see here today, teleportation, dense coding, these are definitely communication protocols, but that doesn't mean that you cannot use entanglement for computation. I mean, there is a lot of use of entanglement in computation as well. And I'm coming to this, that how to understand which one Alice and Bob can apply. Yeah. Okay. If ancilla entangled to a qubit of entangled Bell state is measured, will it collapse the Bell state as well? So this is an interesting question. I mean, so there is something called monogamy of entanglement. If an entangled state is maximally entangled, like Bell state, you cannot entangle it with anything outside this system. So if you are thinking of a Bell state, it is not possible to have a Bell state and entangled it with a third qubit or something like that. But in general, I think if you ask for a general entangled state and not a Bell state, um, if you ask for a general entangled state and not a Bell state, then you can actually measure the ancilla qubit and collapse the part of this, and this is actually used in error correction. I'm not in we cannot really go deep into that today, but what is yeah, I'm not sharing the screen, please. Yeah, give me some time to read through the questions. um, in error correction, what is done is that the original data qubits are actually coupled with the ancilla qubit. And then when you measure the ancilla qubit, it gives you some information about the state of the original system, and it collapses the original system as well. So that is possible. But if you think of Bell state, it is not possible. exact difference between Bell state and entanglement. So if so, okay, let me now share, and there are these two questions. It will be easier to uh, show by sharing. So what we saw here is that this state is entangled. This particular state that I am showing here, this is entangled, but this does not remain entangled if you measure it in, say, plus minus basis instead of 0, 1 basis. If a particular state remains entangled in any basis that you measure, 2-qubit system, then that's a maximally entangled state. So it's also called a Bell state. So you can have entangled state. Entangled state can be anything. Bell state is a special case of entangled state, which remains entangled in every spin direction. All entangled states need not remain entangled in every spin direction. And the other question was how to understand to go from one to other. So let's look into this. The way we were doing is that I need to make it minus. So that means I need to apply a Z gate. And if I apply the Z gate on the first qubit, it works. If I apply it on the second qubit, it also works. So both Alice and Bob can do it. Similarly, if I want to go from here to here, say I need to change the second qubit from 0 to 1 and from 1 to 0. So I need to apply an X gate. Ideally, Bob should apply the X gate because the change is in second qubit. But if Alice applies the X gate, then also it becomes 1, 0 plus 0, 1. So it's not a problem. So this is the way we kind of understand which gates to apply, and what we understand, what is the main take home message from here is that you can always go from one Bell state to the other using only Pauli operations, and either Alice can do it or Bob can do it. It doesn't matter who is doing it. Okay, awesome. Really great that you guys are following and having so many questions. So let's come to this idea of quantum teleportation. Um, so this is a circuit description that I got from this IBM quantum learning platform. You should definitely look into there also. Um, the premise is something like this. So this has nothing to do with Star Trek or something where a person vanishes from one portion and appears in another portion, but it has some kind of similar flavor. So first is the premise is that Alice and Bob are sitting in two different labs and they are in different locations. Alice has prepared some qubit, some A0 plus B1, a single qubit, and Alice wants to send this to Bob. How will she do that? So there is another thing is that sometimes back Alice and Bob had met and they have prepared this Bell state, maximally entangled state of this form. So now Alice has the first qubit of this Bell state, Bob has the second qubit of this Bell state. Using this, can Alice, using this as the resource, can Alice send this single qubit to Bob, who is in a different location? So this is the idea of quantum teleportation. If we pictorially see how it looks like, so this is the entangled pair, say this is with Alice, this is with Bob, and again they are on different locations. Alice has this another qubit, A0 plus B1. What will Alice do is Alice will first measure these two qubits in the Bell basis. And Alice will get the outcome, any one of these four outcomes. How many bits do I need to convey four messages? 2 bits, classical bits. So if I have four messages and if I want to tell you which one of these four occurred, I need 2 bits to convey that message. So Alice will send these two classical bits of communication to Bob. It can be as simple as just taking up the mobile phone, ringing Bob's number and telling him 01. That will sound very awkward if I call someone and say, 01. uh, but anyway, something like that. Alice will do something like that. And depending on whether Alice calls and says 01 or 10 or 11 or 00, Bob will apply a particular unitary on on this qubit. And all I am claiming is that if you do this, Bob will have this state. So let's see what exactly happens. I won't go into the exact mathematics of this. It would be just too cumbersome if we see that how to write it down in Bell state. But you can understand from the previous example that we saw and that we argued that this forms a basis. So if you have a 2-qubit system, you can always represent that as a linear combination of these Bell states. So what Alice will do, so here Alice has this 1 qubit from the entangled state and she wants to send this. Alice measures the 2 qubits in Bell state, and this is what happens. Alice can get one of these 4 outcomes, and depending on the outcome, this will be the qubit state. So for example, the original qubit was A0 plus B1. So if the measurement outcome is psi plus, Alice ends up with A1 minus B0. How to convert from, not Alice, sorry, the Bob's qubit becomes this, because Alice has measured, sorry for that, Alice has measured these 2 qubits and in the Bell basis. So Alice's qubit has any one of these 4, nothing else. It's the Bob's qubit that gets changed. So if say let's take an easier one. If Alice gets the outcome psi minus, then Bob is in this kind of state. So what does Bob need to do? Bob can apply an X gate, then it becomes A0 plus B1. If Alice is in this state phi plus, then this is the state of Bob. What does Bob need to do? Apply a Z gate, it becomes A0 plus B1. Similarly, if it is psi minus, it nothing to do, it's the exact state. So Bob kind of applies an identity, and here Bob applies an X and Z. So this is the reason Bob needs to know which one of these 4 occurred, because accordingly Bob needs a correction at his end. So this is precisely what we discussed, that Alice will send 2 classical bits to Bob, and knowing that outcome, so let's say that Bob has previously created this table, and therefore Bob knows that depending on the 2 bits, so say there is the understanding between Alice and Bob that if the outcome is phi plus, Alice will say 0 0. If it is psi plus, if it is psi minus, Alice will say 0 1. This one 1 0. This one 1 1. So when Bob gets this information, Bob applies a unitary operation, which is kind of a correction. And as you can see, everything is occurring on Bob's end here. Nothing occurs on Alice's end. Everything is identity on Alice's end. So the operations are on Bob's end, and applying the correction, Bob gets the corrected state. So that's all about teleportation. But we will ask 2 more questions here. Technically, I have written 2 questions. We will ask 3 questions here. Question 1. So Alice and Bob, I said they share a Bell state. Okay, let's have a question 1.1. What if Alice didn't share the Bell state, say, psi plus? So I think what we were discussing, this state is 1 over root 2 0 0 plus 1 1. Say Alice and Bob shares 1 over root 2 0 1 plus 1 0. Will teleportation still work? Any thoughts? If this is not 1 over root 2 0 0 plus 1 1, if it is 1 over root 2 0 1 plus 1 0, or 0 1 minus 1 0, 0 0 minus 1 1, will teleportation still work? One answer is no, yes, yes, okay. Yes, most of the answers are coming yes. Definitely it will work, but this table will change. This table will change because now, depending on the outcome, the state of the qubits can change. So the correction that Bob needs to make will change. So this table that Alice and Bob actually shares beforehand, Bob knows precisely what correction to make. This table depends on the particular Bell state that gets shared. So this table I have written considering that the shared state was 0, 0 plus 1, 1. If you try it out with 0, 1 plus 1, 0, the table will be slightly different, but teleportation is possible. Let's ask a second question which was not there. This was the scenario, right? Is it possible? It is definitely not possible using this protocol, because once Alice measures these, she will have one of these 4 Bell states. So she no longer have this shy with her. It gets prepared at Bob's end. Do you think it is possible to come up with some teleportation protocol, not this one, something else maybe, where Alice will be able to retain this state and this state will also get prepared in Bob's end? Because what is happening here, since Alice is getting one of these 4 outcomes, she has actually lost this qubit. This qubit has been lost. Is it possible that maybe I can come up with a better teleportation protocol where Alice will be able to retain this state, but Bob will also have this state? It will not get destroyed here. Yeah, that's actually the correct answer. It's not possible because then it means Alice has been able to create a copy of this to Bob. That violates no cloning theorem. So you cannot have any protocol, not only this teleportation, you cannot have any protocol where Alice also has this state and Bob also gets this state, because that means this is a copying machine. But no cloning theorem does not allow that. So it is not possible. Let's come to this question. Can I perform teleportation with a non-maximally entangled state? Yes, the answer is definitely no. The reason is that Bell states form a basis. So I can measure in that basis. Non-maximally entangled states doesn't form a basis, but probabilistic teleportation is possible. So you can create a protocol where you share non-maximally entangled states. With some probability, the teleportation may work out, but there will be some probability where your teleportation will completely fail. Last question on teleportation. Can I do teleportation without this classical bit communication between Alice and Bob? So I said that Alice needs to pick up the phone and say 00 or 01, something like that. Can I avoid this classical communication? Okay, so we have 3 yes, 4 yes, 1 no, 2 no. Okay, no is gaining momentum. Yes is catching up again. So the answer to this is no. See, if I can do that, if I can do teleportation without classical communication. So remember something that I was telling in the beginning, it is not just a joke here that Alice can be on Earth and Bob can be on Pluto. So if Alice is able to do something at her end and Bob immediately gets the correct state, that is faster than the speed of light. And if you say that, okay, no, the amount of time it will take for Alice to measure and everything, that is not faster, I will say that, okay, this galaxy Andromeda. If you say it is not even, then I'll just start naming. I'll have to Google what are more distant galaxies, but I'll start naming galaxies. So if you can do this without classical communication, then you are somehow able to send information faster than light. So it will violate the theory of relativity. On the other hand, the fact that I need to pick up a phone and tell you this information, that communication cannot happen faster than the speed of light. So this classical communication ensures that teleportation is at par with theory of relativity. But there is a protocol that if you know A and B, so I don't know how many of you actually carefully noticed this, but I kind of said in the beginning that A and B are unknown. In the beginning, A and B are unknown. But if you know A and B, then you still need classical communication, but instead of 2 bits of classical communication, you can do it away with 1 bit of classical communication. It is called remote state preparation, and it is a protocol by Arun Pati. I hope many of you have heard his name. He is one of the great quantum researchers from India. This is a protocol from Arun Pati that's called the remote state preparation. That if you know A and B, you still need the classical communication because this is still valid with, I mean, this is still at par with relativity. But a single bit of classical communication is sufficient. Okay, awesome. Yeah, thanks a lot for really being there in the chat. Let's come to this thing called super dense coding. So super dense coding, the way I like to think of it, it's like the complement of what teleportation is doing. Teleportation is using uh, entanglement to send quantum information, and here I will use entanglement to send classical information. This is super dense coding. So before we go into that, let's ask us this question. How many bits of classical information can be stored in 1 qubit? Any thoughts? So we know that a single qubit can be in a superposition state and everything. Yeah, it can be both 0 and 1 at the same time and all. We know all of these things. Right. You know what I am doing at this point is what Amitabh Bachchan does in KBC. Kind of guides you towards wrong solution. So see, it's true that infinity. Okay, that's a very interesting answer. So it's true that using a qubit and by tuning alpha and beta, you can technically have infinitely many systems. The way we say is that it's kind of both 0 and 1 at the same time. But to get the information, eventually you have to measure. When you measure, it will collapse to 0 or 1. That's all. So someone in the beginning said 1. So using only a single qubit, you can store 1 bit of classical information. And this is something called a Holevo bound in quantum information. But the intuition is something like this, that irrespective of if I created alpha 0 plus beta 1, whatever alpha and beta may be, we need to eventually measure and we end up getting just one state. Okay, fine. Second question. So the fact is that if I send you 1 bit of 1 qubit, I cannot send you more than 1 bit of classical information. Let's call it a C bit. C bit is classical bit and qubit is quantum bit. E bit will be entangled bit. Just some terminology. So what we have understood intuitively is that if I send you 1 qubit, I can only convey 1 C bit of information. Let's ask the second question, which may sound very silly or funny at this moment. So I need to send you 2 C-bits of information. So let's say that there are 2 cricket matches that are coming, and I want to tell you the outcome of both the cricket matches because maybe for some reason you are unable to follow and everything. I have said that, okay, if my bit is 0, then say it's some India versus Pakistan match or something. If bit is 0, then India won. If bit is 1, then Pakistan has won. So I need 2 bits of classical information, right? Now the question is it possible that, so the matches are starting tomorrow. Let's say tomorrow is one match, the day after tomorrow is another match. I'll send you 1 classical bit today or a qubit today, and I will send you the second qubit after the 2 matches. Can I still reliably convey both of the information who won on which match? Do you think it's possible? No? Yes, definitely it's not possible because I am sending one information before the event even occurred. So it is not possible for me to convey the information reliably for both the cases. So the answer is no. And it is very important that we get this apparently silly question. This apparently silly question that two events are happening in the future. I am sending you one bit in the past, one bit after the events have occurred. I cannot reliably tell you the outcome of both the events using this. But this apparently silly thing can be done if I share one bit of entanglement with you. That is technically super dense coding. The reason it's called dense is because we have understood that one quantum bit can store one classical bit of information only. But if I share an entanglement with you beforehand, then by using the entanglement as a resource, I can send one qubit and convey two classical bits of information. That is why it is called dense, super dense. The reason it's called super dense. The idea is very simple. Once more, here is Alice, here is Bob. They share an entangled pair, and Bob has two bits. Sorry, Alice has two bits of information, B1, B2. Alice will apply some Pauli operation on this, IXYZ, on this qubit, depending on what the values of B1 and B2 are. And then Alice will share this qubit with Bob. So at this point, the funny thing is you are not allowed to ask how will Alice share this qubit, because that's not part of the protocol. It can be a teleportation on its own. Uh, it can be that Alice has some superpower. She will just catch the qubit and throw it to Bob. However way you think of it, Alice will send her qubit to Bob. So Bob now has two qubits. Bob will measure them in Bell basis. And the outcome of these Bell basis, now there are two bits of information, will tell Bob about B1 and B2. That's super dense coding. I'll once more come back to this. We won't spend time on this now, but I'll once more come back to this just to remind that between Bell basis, I can go from any Bell state to any other Bell state using Pauli operations, and any one of Alice or Bob can do it. That's sufficient. This information is very important. So let's come to this point. Let's say that Alice and Bob share this entangled state. Alice can have two bits. So these are the four possible values that Alice can want to share. And these are the operations that Alice will do at her end. See, everything is happening at Alice's end now. Nothing is happening at Bob's end. Alice is using the one qubit, this first qubit of the entangled pair. Alice is applying one of these four operations. What happens to the resultant state? So I have started with this. Alice didn't do anything, so it remains the same. I have started with this. Alice applied X gate, so this becomes 0, 1 plus 1, 0. I mean, you can say 1, 0 plus 0, 1, but it's kind of the same thing. Alice applies Z gate. What happens? It becomes 0, 0 minus 1, 1. Alice applies the Y gate. It becomes 0, 1 minus 1, 0. Now Alice has taken her qubit and sent it to Bob as well. So Bob now has both the qubits here. So what will Bob do? Bob can measure in Bell basis, and Bob will get any one of these four outcomes. Now see what has happened. If Alice wanted to send the information 0, 1, say on first match India has won, on second match Pakistan has won. Yeah, I shouldn't be saying things like that. But anyway, say the first match India has won, second match Pakistan has won. Alice will apply this, and this is the state. So it is never like that all four of them can happen simultaneously. Depending on the bit that Alice is trying to convey, Alice will apply the operation, and this will be the state. So when Bob measures in Bell basis, he will deterministically get one of these four outcomes, because if this is the state, then if this is the bits, this is the state. So when the measurement is there, this state will come up 100% of the time with probability 1. There is no probability, any other probability here. So now what the inference will be, because Alice and Bob have previously discussed that, okay, if if this happens, I'll do this. These things are already discussed between Alice and Bob. So the inferences Bob will measure in Bell basis, he will deterministically get one of the outcomes, and he can actually get the 2 bits of information that Alice wanted to share. So what has happened? See, if you just naively think of dense coding, it won't make too much, sorry, this will be 1 over square root. It won't make too much of sense immediately, because what it is saying is that there are eventually 2 quantum bits and 2 classical bits of information. But think of this, these 2 quantum bits are shared between Alice and Bob sometimes in the past. So even before the events occurred, even before the matches have begun, Alice and Bob have shared the qubits. So it is the question that I asked in the beginning. Alice has somehow sent 1 qubit to Bob, which is, say, this second qubit here, and that has happened before the matches were even played. Once the matches were played, Alice applies the operation
Sir,
accordingly, and
sorry to bother you.
yeah.
Sir, kindly take 5 minute breaks so that we
Yes, yes.
can change the YouTube session.
Just after this slide, we will take the break.
Okay, sir. Okay.
And just after, so where we were, even before the matches were played, Alice and Bob shares this. So one of the 2 qubits is shared with Bob even before the cricket matches were played. Once the cricket match was played, Alice applies some operation on them and sends the second bit to Bob. And now Bob does a measurement in Bell basis and he can get the information. So it conforms to the second question that we talked about, that can you send 2 bits of information if you share 1 bit before the cricket matches were even started and the second bit after both the matches were played? The answer classically was no. The answer mechanically is yes. So that's why it's so interesting. That's why it's called the super dense coding. That this is something, this is not exactly sharing 2 bits of information with 1 qubit, but it is doing something beyond what was possible classically. So yeah, let us stop here. We will come back with the CHSH game, which kind of, so as I started in the beginning, that Einstein had this reservation that all these entanglement and everything, that you cannot represent this properly, you cannot give the mathematical expression of the 2 qubits. All of these are happening because your quantum theory is incomplete. So that was Einstein's point of view, and we will see that it is not the case when we come back. So yeah, let's have some break and come back. Okay, let's have some break and we can take the questions after the break so that everyone is